Hello everyone. In the last class we discussed about the optical fiber, how it is constructed, and we derived the derivation for the numerical aperture, and also what is the condition required for the light signal to travel inside the optical fiber. So that and all we discussed, and so the fractional index change, and what is the that V number, what is the expression for that we all get to know. So now what is the relation between the numerical aperture and fractional index change? So there is one small expression, just we will find out now. So relation between numerical aperture and fractional index change. So what is the relation between fractional index change? So we know that what is the expression for the numerical aperture. So that is we know that numerical aperture is equal to root of n1 square minus n2 square, right? And what is the fractional index change? So that is for that how we are representing, that is delta is equal to the difference between the refractive index of the core and cladding to the core refractive index of the core. So just make the rearrangement of that. Delta n1 is equal to n1 minus n2. Okay, so now again take this numerical aperture expression, just expand that, then what we will get, n1 square minus n2 square. So this is in the form of a square minus b square. So we can write this n1 plus n2 into n1 minus n2. Okay, so but n1 minus n2 is what that how we can relate the numerical aperture and fractional index change. So n1 minus n2 is delta n1. So just substitute that, then what we will get, this n1 plus n2 is into delta n1. So numerical aperture. But when the refractive index of some cases the refractive index of the core that is equal to the refractive index of the cladding. Suppose it is like that, then what is the expression we used to get? So if n1 is nearly equal to n2, n1 is nearly equal to n2, then what we will get, so this equation will become numerical aperture is equal to root of 2n1 delta n1. Okay, so then numerical aperture is equal to root of, this will become root of 2n1 square delta. So if we take this n1 square outside the square root, then what we will get? We'll get n1, that is n1 root of 2 delta. So this is the relation between the numerical aperture and fractional index change for the optical fiber. So the next concept is the types of optical fiber. So what are the types of optical fiber? So how the light will propagate inside that optical fiber, and how it is structured, or how it is constructed, so that we will study now. So types of optical fibers. So optical fiber, it is classified into mainly 3 types. Okay, so that is based on the number of modes can pass inside the optical fiber. The number of light ray signals can pass inside the optical fiber. So types of optical fiber. Types of optical fiber, mainly three types of optical fiber. So step index, single mode optical fiber. Step index, single mode optical fiber. So that means here in this case of optical fiber, the single ray of light will travel inside the optical fiber. So, and next, if the number of modes will increase, so then the next is step index multi-mode multi-mode optical fiber. And then next last one is graded. So here the number of light ray signals will increase, is more than the one. And then one more, that is graded index multi-mode optical fiber. So this is also called as a green. So this is represented by green. Okay. So like this, three types are classified as a different types of optical. So that's why the optical fiber, this is based on the number of modes which can travel inside the optical fiber. So classified into mainly three types. So step index single mode optical fiber, step index multi-mode optical fiber, and graded index multi-mode. So now we will let us study one by one. What is this single mode? Step index single mode optical fiber means how it is constructed. So that is depending upon the diameter of the core and cladding. So first we will study step index single mode optical fiber. So this is step index single mode optical fiber. So it is constructed like this. That is, this is the core, inside is core and the outside is cladding. So the core, it is inside, that is, it's made up of the refractive index of N1 and it is cladding is with the refractive index of N2. And its diameter, the core diameter is 8 to 10 micrometer and the cladding diameter is 60 to 70 micrometer. So that the ray of propagation, that is depending upon the diameter of the core and cladding also. Always the core of the core, the refractive index of the core, it must greater than the refractive index of the cladding, and the refractive index is always here in this case it is a N1 refractive index, it must be greater than the N2, then only the complete total internal reflection will takes place inside the optical fiber. Okay, so inside, that is, it is made up of a core and the outside is cladding. So in this, so when a ray of light will pass inside the optical fiber, so then the total internal reflection will take place, that ray of light will completely reflect inside the optical fiber and that will process the signals. So that's why here only the single mode of light signal will pass. Only the single mode of optical light signal will pass inside the optical fiber. That is, so that's why we used to call this is a step index single mode optical fiber. So the diameter for first initially, the diameter of the core, is 8 to 10 micrometer. and the cladding, the diameter of the cladding is 60 to 70 micrometer. Okay. So then it will propagate only the single ray of light inside the optical fiber. So that's why it is called as the step index single mode of optical fiber. And here the core refractive index is N1 and the cladding refractive index is N2. So here the refractive index of the core is always greater than the refractive index of the cladding. Diameter of the core and the cladding is over. So the next, the refractive index of the N1 is greater than the refractive index of the N2. So then only the total internal reflection will takes place inside the optical fiber. But as soon as the light signals will pass inside the optical fiber, at some cases the refractive index of the N1, as the light rays is propagating, but at the interface of the core and cladding there is a sudden change in the refractive index of the optical fiber. So as soon as light signal is passing inside the optical fiber, so when it is goes on at the interface, the refractive index of the both N1 and N2, there is a sudden changes. Okay, first initially the core refractive index must be greater, but as soon as light signal passing at some point, so there is a sudden change in the refractive index of the core and cladding at the interface. So then the light signal that will take a step-like structure. So that's why then the refractive index profile is like this. That will become refractive index profile is like this. So that what is the distance? This is the radial distance. So refractive, there is a sudden change in the refractive index of core and cladding. Change in the refractive index of core and cladding at interface. So that's why it will take a step-like structure. Hence refractive index profile, step-like structure. So that's why step-like structure. And as soon as here the diameter of the core that is very narrow, so that's why only the one ray of light signal can pass inside the core. Okay, compared to the cladding, so it is very narrow in structure. Okay, so that's why it can allow only the one single ray of light inside the optical fiber. So like this it is considered. Then what are the applications, what are the merits for? So the merits, that is it can 80% in use, because so we can transfer the light signal for a longer distance. It's having a higher bandwidth, so there is no dispersion due to only one single ray of light signal is passing, so there is no dispersion of the signal, there is no loss of signal. So that's why the light signals can carry through for a longer distance. So that's why it is used in the submarine cables. So that is the connection, telecommunications between the sea. So that's why it's having a long bandwidth. So and that's why it is used maximum 80% compared to other optical fiber. So 80% this optical fiber is used in the for the telecommunications purposes, and less expensive also, because so it's easily can compared to other optical fibers, so this is less expensive. So that's why 80% of people use this single mode optical fiber. So merits is, we can say that having a higher bandwidth. Having higher bandwidth, so that's why there is no dispersion, there is no loss of the signal inside the optical fiber. And also the speed of this signal is unmatched compared to the other optical fibers. So that's why it's having higher bandwidth. And then so but the demerits, what are the demerits of this optical fiber? It's very difficult for the joining, that is for splicing. The splicing is very difficult because if something happens, if there's something damages the parts, then we can't able to join the parts and it won't work with that efficiency. So that's why here the splicing is very difficult. So splicing is difficult. Splicing is difficult. So that is, joining is difficult. And what is the source? So the source of the optical fiber is laser or LED. Okay, so we can pause inside the what is the light, laser light can pause, or LED inside the optical fiber. And applications. So this is used in the submarine cables. So application, this is used in the submarine cable system, so that helps to telecommunication between the ocean and sea. So due to having the higher bandwidth, so we can transfer the signals for a longer distance. So these are the applications and the construction of the optical fiber. So and also merits, this is 80% of the people, 80% used in for daily telecommunication, 80% used. And also less expensive, so easily affordable compared to others. So this is about the optical fiber. Single step index, single mode optical. So step index, that indicates that it's only the single ray is passing inside the optical fiber because of due to narrow. So that's why it will take a step-like structure inside the optical fiber. So this is a step index, single mode optical fiber. So the second one is step index multi-mode optical fiber. Okay, so the next is step index multi-mode optical fiber. So here it is made up of, the core is little bigger compared to in step index single mode optical fiber. So its core, the diameter of the core is 50 to 200 micrometer. The diameter of the core is 50 to 200 micrometer. Core is 50 to 200 micrometer. Okay, and cladding, and the diameter of the cladding is 100 to 250 micrometer. 100 to 250 micrometer. And the core refractive index, it is made up of the core represented by N1, and the cladding refractive index, it is represented by N2. And compare it here, what will happen? So here also the refractive index of the core and cladding are uniform. At initially it will be uniform, and here what is that, N1 refractive index of is always greater than the N2. So the core refractive index, it must be greater than the refractive index of the cladding. So then only the complete total internal reflection will take place inside. So that's why here that condition is N1 is greater than N2. Refractive index of N1 is greater than N2. And here also, as there is a sudden change in the refractive index of the core and cladding at the interface, then what will happen? It will take a step-like structure. Okay. The refractive index profile will take a step-like structure when there is a sudden changes in the refractive index of the core and cladding. So at the time it will take a step-like structure in the refractive index profile. Then due to here the comparison of the diameter is bigger compared to single mode optical fiber. So that's why here there is a multiple rays will travel inside the optical fiber. So that is more than one rays can travel inside the optical fiber. So that is due to the diameter of the core is more compared to in first type of optical fiber. And then the merits, this also is having a less expansive, and but due to this having compared to that single mode optical fiber, this having a lower bandwidth. So that's why due to that lower bandwidth, so this optical fiber is used for the shorter distance, used for telecommunication in a shorter distance. So this multimode optical fiber is used for telecommunication purposes, but at a shorter distance, due to the having a lower bandwidth. This optical fiber is compared to that, it is the least expensive. So there is merits, least expensive. And what is about demerits? So due to the multiple mode of optical signal, light signal, there is a dispersion will takes place inside the optical fiber. That is a loss of signals will happen inside the optical fiber due to the shorter bandwidth, and also due to lower bandwidth it will transfer degradation of light degradation of signals will take place. Degradation of signals, that is due to, and the attenuation due to multiple rays of signal rays, and this is not suitable for longer distance. So that's why this is having a lower bandwidth compared to the step index single mode optical fiber. So this because if the number of rays are together passing inside the optical fiber, means there is a loss of the signals will happen, that is due to, and also attenuation. That is attenuation means the strength of the signals may be decreased due to the collision inside the optical fiber. Much maximum used, it is less use compared to the single mode optical fiber. Same here also, the source of light is laser or LED. So that's why this is used applications used in to link the for application for say for communication purpose only, but for the link the lower bandwidth requirements. Link between the link for lower bandwidth requirements. So it will collect the, it will transfer the information within the for the lower bandwidth requirements, where it is required only for a shorter distance. It will transfer the signals. So that is the application of this multimode optical fiber. And here also same, the splicing is difficulty. If any damages happen due to the rain and all, it's difficult to splice the parts, so that's why it's also expensive. But compared to the single mode optical fiber, so this is least expensive.